Right, two-level models for complex survey data, plausible values. So let's just move this so you can actually see, hopefully. So this first session, so the outline is I'm really going to obviously introduce what plausible values are, but quickly shift into a PISA data example. Who uses PISA here? Great. I started using PISA about 2 weeks ago. So we can co-learn together. I can hopefully give some multi-level stuff and you can tell me, well, you should have done this, you should have done that. And that's great. Please ask questions at any point at this interrupt. We're going to use the PISA 2018 data United Kingdom sample, which has data from England, Scotland, Wales, and Northern Ireland. We're then going to look at different approaches to using these plausible values. So what we'll see is we're going to analyze students' maths achievement or their maths skills scores. Rather than getting one test score, if you like, we have 10. Okay, so what on earth do you do with that? Different people, if you read the literature, people do different things. Okay, and there's a number of invalid approaches. So one approach, and some are worse than others, okay? So one approach is to only analyze one of the plausible values, the first one. Yeah. So we'll look at that. Well, then that will lead us into the kind of the valid approach, which is to repeat your analyses separately on each of the 10 plausible values. You'll get 10 sets of results for your regression model. You then need to combine those results using Rubin's rules, which have been developed for analyzing multiply imputed data. Okay, so we'll look at that and I'll explain it in a bit more detail. And that all seems quite complicated. It sounds complicated, right? So then you think, well, why don't I just take the 10 values and just average them and analyze that? Okay, so that's another no-no. So we'll look at that and what happens and how the results differ when you do this. And at the end, you might go, well, I love multi-level models. If I've got 10 plausible values per student, why don't I stack them within the individual? So I have 10 measurements at level 1, within students at level 2, within schools at level 3. It's a 3-level model. Yeah, it's also wrong. Okay, so we're going to look at the correct approach, 3 incorrect approaches, and just see, does it make a difference in practice? Okay. Because often, you know, these kinds of things, you're just like, they're kind of a bit geeky, right? It's kind of interesting if you're into the methods, but does it really make a difference in practice? And in some ways, it feels like the PISA data almost it's become so complex that it devalues it. It makes it inaccessible to people. People do the wrong things, and PISA say, no, you have to do it. You have to do this, this, and this with the weights and the plausible values, and you've got to fit 80 of these balanced replication, repeated replication weights. I'm not talking about that today. There's another kind of thing going on. There's so much complexity, like statisticians have taken over, right? So it's kind of useful to see what actually happens in practice if you do some of the incorrect approaches. You can't be perfect. Okay. So, yeah, I'm going to talk about PISA, but you'll see these plausible values in other large-scale education assessments like TIMSS. And why are plausible values published in the first place? So, essentially, we're trying to test a cohort of students on their maths skills. Okay, so you make them do a maths test. Okay, there's a limited amount of time to do all the PISA assessments. And so the student will get a limited number of items, questions on the test. Let's say they get, I'm making this up, 20 questions. You cannot hope to survey the full domain of math skills for 20 questions. Okay, so what you're going to get back is something which is estimated with error. It's an estimate of your maths ability, but it's very uncertain. We've only got these 20 questions. Furthermore, different students get different test book lists. And so not all students do the same maths test. And that's kind of, partly that's deliberate. You've been for the cohort as a whole, so cover more of the maths curriculum, you get different students doing different bits of it, okay, at random. Okay, and this introduces a lot of complexity. So, you know, in an ideal world, you'd make a student do all 600 questions, and then you get a wonderful, very precise maths score covering everything. It's not practical. Okay, so they've got these small snapshots. So we've got to respect the error in the math score which comes back, if you like. And that's what the plausible values are trying to do. So each student has 10 plausible values. They take different values for your math ability, And that variability is communicating to you the uncertainty in the estimation process. Again, that needs to be propagated into the analysis. If you have to make just an analysis based on one of those scores, you're treating that one score as if it's a truth. It's not a true score. It's an observed score with a lot of measurement error because there's not many maths questions. It's not like national examinations where you do 2 different exam papers of 2 hours and 3 hours, 5 hours of assessment. You know, all of the assessments for PISA are just done in a couple of hours of covering reading, maths, science. Okay, very different type of testing. Okay, so yeah, and underneath the bonnet, they're using something called an item response theory model to produce estimates of student ability. This is like a fancy logistic regression. Did you answer question 1 correct? Yes, no. Did you answer question 2 correct? Yes, no. It's like a binary outcome, logistic regression, and it's like a 2-level logistic regression. Items within students, and you get estimated student ability. And the plausible values come off the back of this IRT model. So, so essentially, you can think of these 2 plausible values capturing the measurement error. Yeah, the measurement error in math scores because you have so few items. Yeah, the more items there are, the less measurement error, the more the plausible values will coincide and collapse down to 1. And if they did collapse down to 1, you could analyze that 1 score. But that's not the case. They're very varied. Okay. And this means quite peculiar things. 2 students who gave exactly the same responses to the common maths test, okay, will nevertheless have different plausible values. So these plausible values are drawn at random from the probability distribution for that student's ability. Okay, so you two students, 20 items on the test. Item 1, you both answered identically. Item 2, you both answered identically all the way through. You're identical in terms of what you responded. Nevertheless, your 10 plausible values will differ from your 10. The average of your 10 will differ from the average of your 10. You look like you have different abilities. Okay, so PISA is not to be used for making statements about individuals. Okay? It's only worth making these aggregate comparisons for studying countries. It's not about studying the individual. Okay, so there's some quite weird things going on here with plausible values. So let's shift into the PISA data example. So I'm going to look at the PISA data for United Kingdom. So PISA is for 15-year-olds. It's not really kind of a maths test like we do in school. It's more about your maths skills in the wider world. Maybe questions about your financial literacy and maths and practice for real-world sessions. So the data have 13,818 students within 471 schools. So that's a 2-level data structure, students within schools. And then we have these 10 plausible values. So let's start looking at the data and get a bit more into it. Right, so here is a data frame. You can think of this like the Excel spreadsheet view of the data. And I'll show you one of these for each of the data sets. And what you can see here is the different columns of the different variables in the data, the different rows of the different students. So my first column here is the level 2 identifier, okay, which is the school ID. And I'm using the PISA name up there, which is country school ID, if you look at it. We're going to use notation J to index the schools. The second column are the student identifier. We use the index I. And then we have our response. You might say dependent variable outcome. These are synonyms. We've got 10 of them. Okay, here are the 10 plausible values. Okay, so PV1, PV2, through to PV10 for maths. I use Y for my dependent variable, subscript IJ for student I and school J. The superscript 1, 2, through 10 indexes the plausible values. That's the notation we're going to use. And at the end, we have one explanatory variable. Multi-level models will be very simple, okay, because the easy bit is to add more explanatory variables. So I'm going to keep that simple. I just got a dummy variable for whether the student is female. Yes, no. X for explanatory variables. IJ because it's a characteristic of the I, the students within the schools. J varies within the schools. Okay, so you see the very first line of data, the student's first plausible value is a score of 209.7. The second one is 301.8. The 10th is 430.7. They're all over the place. Yeah. So we've got 10 of these values for the students. So what is their maths ability? These are 10 plausible values. These are 10 kind of random draws from your kind of probability distribution for what the true score is. It's kind of a weird concept. Who's done kind of multiple imputation here? Yeah, so multiple imputation, you might have a variable like income and it's missing for some of your people. And so you try and impute it. And you build a imputation model. Income is predicted by all these other things which you do observe in people. Okay, and off the back of that model, you generate 10 plausible, 10 imputed values. Okay, it's the same idea. And so if this was income, these would be 10 guesses for what a person's income is based on all the other information that you do observe. Plausible values, it's exactly the same mechanics to it, if you like. But if you like, for plausible values, it's like your math score is missing for everybody. Yeah? We don't observe anyone's math score, but we're able to predict it with uncertainty for everybody. And this is the uncertainty. There's this variation across the course. So it's a really nice, if you're familiar with missing data and multiple imputation, it's really nice seeing that link. Clearly, if there's no measurement error, those 10 values will be the same and would be identical, but we've got substantial measurement error. So let's look at some descriptive statistics. Here are the means, the standard deviations, and the correlation matrix for the plausible values. So PISA is on some weird and wonderful scale. So the mean math score in the United Kingdom, when we do it for the first plausible value, is 496.7, for the second 494.0, and so on. So even at the country level, when we're averaging these 13,000 values across the students, you still see the mean is moving around and you shift from one plausible value to the next. Standard deviation is around 90. And here's the correlation matrix. The correlations between those 10 plausible values is only around 0.8. Yeah. That means, okay, that 20% of the variation in this score is measurement error in these scores. Okay, so measurement error is big. Okay, and it's because each student is only doing a limited number of items, and you don't get that much precision off the back of it. Okay. So yeah, we need to do something about this. We can't just analyze one score in isolation. So it's really, for me, that was really interesting when I saw just how weak those correlations are. They're not kind of 0.95, 0.99, 0.8. Yeah. Right. So let's shift into our model of interest, which is within multi-level modeling, it's trivially simple because it's a two-level analysis of a continuous outcome with one explanatory variable, another explanatory variable that's female. Right. Because it's our first model, let's go through it. So we've got the math score, and this is what I want to estimate. I don't have a variable called math, okay, because I don't observe students' true maths ability. If I did, this is what I'd do. I'd regress their true maths score for student I on school J on an intercept, and because of the female variable, beta 0 will be the mean score for boys, plus beta 1 times the female dummy. Beta 1 is the gender gap, girl minus boy gender differential. How much higher do girls score than boys on average across all schools and students? The mean math score is going to vary across the schools. The UJ is going to pick that up. Okay, these are school random intercept effects. They allow the school mean to be higher or lower than the overall mean. Okay. And the ERJ are student residuals. They can't perfectly predict students' math scores off the back of this. Standard distributional assumptions for the school effects and student residuals that they're normally distributed in means of zeros and constant variances. These are variance components. The sigma U squared is the between school variance. To what extent does school means vary, having adjusted the gender? Okay, do they vary a lot? Do they vary a little? That parameter sigma U squared will quantify it. And sigma E squared is within schools, how much are the students varying around their school means? We'll estimate that as well. So if we did observe students' maths scores who, that's it, they're done. End of lecture. The problem is we don't observe student math scores. All we observe are these kind of 10 plausible values, these 10 guesses or estimates. Okay, and they're all different. So what are we going to do? So here we go, questions. Any questions at this point? Yeah.
Yeah, it's a silly question.
Yeah, they're the best ones.
Yeah, it's not one module, it's not one PISA. And for that, why they don't actually provide the actual score? What we do have to have at least 10 plausible ones.
Well, I think, yeah, so the students only do a limited number of items. And so the actual score that a student gets is not a kind of, you know, if you gave that, people would analyze it and treat that variable as if it was a true score or measured with no measurement error. In reality, off the back of a limited number of items, you've got a huge amount of measurement error. So maybe to force people into respecting that and taking it into account in their analysis, they don't give you the observed sum score. What they give you is these kind of predicted scores and 10 other. To force you perhaps into doing a proper analysis. The problem is a lot of people don't do a proper analysis. They do one with valid approaches. And then they're using an IRT model as well. But so off the back of the IRT model, they could give you the actual predicted score. But what they're really giving you is the predicted score plus noise, which indicate the measurement error. So I think it's a deliberate action to prevent you from doing naive analysis. But you can still do different types of naive analysis. Yeah. Okay. Essentially, you know, if you average those 10 math scores, you would get close to kind of getting the predicted score which they could have given. Okay, but then if they gave that, you just analyze that and then not realize that it was still measured with error, if you like. Okay, so this is what a lot of people do. It's very tempting, and it's what I would certainly do for model building. You know, you quite quickly want to move around different models, explore what's going on. You can't do the full fanciness in every single model. So let's kind of scope the terrain, work out our series of models, and then at the end, we will do it properly to get correct standard errors and so on. So you might start just by going, well, I don't observe students' math scores, so I'm just going to use the first plausible value. Okay. So we know that plausible value it's got measurement error in. 20% of the variation in that is measurement error. The parameter estimates will be unbiased, the betas, okay, but the standard errors on those regression coefficients will be too small because we've ignored the fact we've got measurement error. We're treating naively this as if it's the truth. So let's see these results. So here are the results. So yeah, I'm presenting to you, and you'll see quite a few of these tables, point estimates and their standard errors. All the models are being fit by maximum likelihood estimation, just like you use in logistic regression, and the standard for multi-level models. So you can see the intercept, which is the mean math score for boys in the UK is 500.1. Relative to boys, girls are scoring on average 9 points less. Remember, a standard deviation was 90. 9 over 90 is 0.1. They're scoring 0.1 of a standard deviation there. For me, that's a meaningful effect. Okay. And then we've got these variance components: school variance, student variance. And if you divide the school variance by the sum of the school and the student variance, you'll get a variance partition coefficient, quantifying what proportion of the unexplained variation in math scores is between those clusters, between the schools, and work out what's within. So between the schools, we've got 20% of variability. Within the school, 80%. So that's going to include measurement error within the school. Yeah, but you can easily just do that and go, oh yeah, it looks all right, that's quite interesting, publish. But this is not good, as you'll see, because on this slide you see, well, I kind of got a bit interested in plausible values, so I just repeated it on the second plausible value, all the way through up to the 10th. Look at my gender gap in red. Minus 9.1 off the first plausible value, minus 9.7 off the second, minus 7. Yeah. And yeah, I haven't shown you here, but for the sixth plausible value, it went down as low as minus 6.5. And for the ninth, it went as high as minus 11.4. This is substantial variation, yeah. So which plausible value you pick leads to different substantive conclusions and potentially different, policy recommendations. Particularly if you're going to tip into significance, non-significance, and if you're using that as a criteria to make the conclusions, which we often are. So I think that just really illustrates that you can't just analyze one plausible value in isolation. You can get quite different results. So in a way, you can think of within any given model, the standard errors are communicating sampling variability, like they always do. But across the models, the fact that the point estimate is varying is communicating measurement error. Okay, because each of these plausible values within it has the true score, but has measurement error as well. We're taking these different draws. And so there's two sources of uncertainty: sampling variability, conventional standard errors, and imputational measurement error variability, the point estimates changing across the models. And we need to get both those sources of uncertainty into our results. And this is going to shift us now into Rubin's rules that are going to combine all of this together, give one set of final point estimates with standard errors, include sampling variability and this measurement error variability. Okay. So, so the correct approach is to apply what are called Rubin's rules in the context of analyzing multiple imputed data sets. Okay. So, I've written here, let theta denote a parameter of interest. Well, our parameter of interest is the gender gap, so you can think of it as beta 1. Okay, that's what we're interested in presenting off the back of our analysis. Okay. Problem is we've got 10 of these values, and they have all different answers, and they're quite different. So what we should report, and this is nice and easy, is the average. You simply average the 10 gender gaps, and that is the point estimate, the final point estimate. Okay. That sounds very easy, and it is. So that's good. Right, so yeah, just the average of minus 9.1, minus 9.7, all the way through to minus 7. Add them up, divide by 10. That's your final point estimate for the gender gap. Standard errors are going to be more complicated. Okay. Again, from 10 separate analyses, we've got 10 standard errors. Let's go and have a look at those. Okay, so here we go, 1.5, 1.4. You should have a few more decimal places. Yeah, for teaching, I've limited it. 1.5, they're moving around. Okay. But each of those standard errors is only communicating sampling variability. Okay, we can't just average those standard errors. We need to bring in back the point estimates are moving around as well, which is the measurement error variation. We need to combine both those sources. Okay, so here we get some scary equations, unlike the previous ones, which are nice ones. So the final standard error, and this is exactly the same as for Rubin's rules, the final standard error of the gender gap is equal to this expression on the right. Okay, so within the square root is the final sampling variance, and you square root the sampling variance to get the standard error. That's what the square root is. So the sampling variance has got two parts. It's got this W part, and it's got this B part. Okay, so the W part is you can think of this as representing the like the average sampling variability, a little bit like that conceptually. Whereas the B bit is getting the measurement error uncertainty. Your two sources of uncertainty, okay, and they're both being brought in. So with standard errors, the way it works is you average the sampling variances, the squared standard errors, okay, mechanically. And there's 10 of those, and so you've averaged it. Now here you can see the point estimates, those gender gaps are varying, okay? And we're saying, well, how does each gender gap vary from the overall average gender gap? Sometimes it's lower than the average of the 10, sometimes it's high, it's varying around. That variation comes off the back of measurement error. every plausible value, that whole point is to propagate that measurement error through. And so this is like calculating the variance, the measurement error variance, okay, and the sampling variance from sampling. And those two things get combined according to Rubin's rules, and that is the correct approach for getting the final standard error. Bit hocus pocus. And the nice thing is the software will do this for you if you use other packages. So in R, and in Stata, we're going to use the multiple imputation commands in Stata to combine the results. Okay, because it's the same technology. In R, I think we do it by first principles. Just because in R, I try and use the base R because things change over time. And if you use the fanciest way of doing things, it will fall apart when you do it 5 years later. Okay. And then both those software packages, there are fancy ways for doing things. I try and do things as simple as possible. So we'll see it in a minute. Okay. That's the hardest approach, right? Which is why people don't necessarily do it, and it looks complicated. You'll see when it comes to the code, it's not complicated in terms of what you do in Stata or in R, but it's complicated to think about and to understand. Yes, on this slide, I'm just making, I've already made this point that we're really just mimicking what one does with multiple imputed data sets and Rubin's rules. Okay, so, and this is just showing you what you get back. Okay, so model 2 is where I've used Rubin's rules to combine results across those 10 separately fitted models to the 10 plausible values. The mean across those 10 point estimates is minus 8.5. The final standard error is 2.2. Look at that 2.2, it's bigger than any of the standard errors you got when doing the separate analyses, right? 1.5, 1.4, 1.5, that's just sampling variability. Once you factor in the measurement error, it's going to go up. Okay. It's gone up to 2.2. Okay. So any given analysis is unbiased. Okay. Yeah, if you did this, these are unbiased results, unbiased results, unbiased results. Okay. But they're spuriously precise because there's no acknowledgement that this is a plausible value and containing 20% measurement error. You're treating it like the truth. And that standard error is reflecting sampling variability, but not measurement error. It's too small. Okay, so the point estimates are unbiased, the standard errors are biased down. Okay, and here, model 2, where we combine results, these are the correct ones, unbiased point estimates and unbiased standard errors, ones which respect the measurement error on top of the sampling variability. Good point for question. Yeah.
No, I was just noticing that the standard errors for everything else has gone up quite a lot as well. But it's like double.
Yeah. So the measurement errors in the outcome, and that affects everything.
Yeah.
Yeah. It's just a load of. It's like taking. You can imagine doing another analysis. Forget PISA where you've got an outcome variable, and there's no measurement error in it. You just add 20% noise and rerun the model and see what happens. That's a good exercise to do. And that's what this plausible value is. It's just got 20% of this noise.
Well, in some ways, with the 10 plausible values, I thought first of all, well, it's kind of like sensitivity testing, right? Like actually, well, you're saying well, there's considerable variation, but actually, like in each case, it's significant. It's in the same direction. It's the same order of magnitude. This is, but actually, if you're doubling the standard error, with using Rubin's rule, then that makes the difference. Yeah, you might. I mean, it might be. Well, I mean, the point estimates did vary. It varied from as low as 6 to as high as 11. So not doubling, but getting there, right? 6.5 up to 11.4, just from 10 draws. I mean, you could have taken 20 draws, and then you'd see an even wider range. Sure. So I'd say there's meaningful variation. There's substantively meaningful variation across the plausible values, which is not for substantive reasons, it's for measurement error reasons. But yes, the fact the standard error goes up could suddenly mean that another coefficient is no longer significant than you thought it was. And so you'd be making different recommendations. So I mean, it depends on what you're looking at. And remember, school level characteristics are estimated with less precision in general. So they're going to be more like the kinds of regression coefficients which would suddenly appear not significant once you respect the measurement error.
That seems echo a little bit. The variance practice is also done change. So it's there 0.1 million, say 0.1. Is that by design, or would you expect there to be a change in the level of variation as the rest of the
yeah, I don't know. Yeah, no, I suppose with some of the things I was saying, I suspect I would have done in a way. Well, I suppose it's not kind of, we're not kind of stripping the measurement error off, because we can't. You know, if I observe the students, I'm unable to get to the true score. We don't observe the true score. So I'm unable to strip it off, but I am able to kind of, if you like, fix up the standard errors in light of it. Maybe that's where to look at it.
But I suppose randomly, managing their randomly is also possible. So I sort of expect it to make the same.
Yeah. So yeah, and there's other approaches you could do here. You could kind of, you could fit a model with like so structural equation modeling frameworks. You can fit models within them. You can specify models with known measurement error, where you declare this variable has measurement error and it's 20%. And so that would be interesting. Another kind of approach you could do. You could do instrumental variables, where you go with two plausible values, use one to instrument the other as another approach to strip off measurement error. So there's many kind of things you could do, and it would be really quite interesting to explore some of those, but they're a bit kind of bespoke. Yeah.
My take home from this would be the approaches. The original approach was relatively robust, right? Because you're getting the direction of it very similar. They're not going to draw a difference from something.
Well, no, I disagree. Look, you pick one of the plausible values, and you pick plausible value 6, and that's a gender gap. Another researcher picked 9. It's almost doubling.
Yeah. So if you're saying 9.1, 7. Yeah. I mean, 2-point difference. Yeah. I mean, you're persuading me that this is definitely worth doing.
Yeah.
And you need to check the standard errors when you get the result. We're not overcoming a result.
No, not here. But I haven't. I just picked gender just because it's a very easy example, right? Maybe with a lot of. It'd be interesting to kind of go through a little bit more systematically and see to what extent the conclusions changed. You could develop some criteria for whether you consider a difference between two numbers as being substantively meaningful or not. And that would be a nice bit of kind of methodological light research where you are really kind of researching the point that you're making. Yes, we should do model 2 where we combine the results. Clearly, that's the correct thing to do. But to what extent does it really matter in practice? And then you could do a whole research paper on that. Because, coming back to what I said earlier, there is something about PISA, which is that statisticians have got a bit carried away, and they're providing a product which is kind of, if you follow all the rules of what you're meant to do, it's kind of excessively complex.
Yeah, I'm waiting into this as well.
If we could do weights with this, multi-level weights and plausible values.
Wondering, there's some differences in opinion on if you're looking at the achievement as the control for a different outcome. So here we're obviously looking at achievement as the dependent variable and just female as the coefficient of interest. But if we're using achievement as just dependent, we're looking at, let's say, dropout or whatever. Choosing one possible value versus trying to figure out this as a control variable. Some people say, okay, well, one possible value is fine. That's not the variable interest, and it captures enough as a control for that. Just want to hear your thoughts on it.
Yeah, I mean, I would have thought that if the math score is an explanatory variable, I would have thought there's more need to worry about these issues. But I think if you think about measurement error in general, measurement error on an explanatory variable is more consequential and attenuation of the regression coefficient than on the outcome. We've got unbiased point estimates. It's only the standard errors which are wrong. I would have thought if it was an explanatory variable, you'd also have biased results. That's got the back of doing one analysis. But try and see. But just think about measurement error more generally. Yeah.
So would you apply the same process, even if it's an explanatory variable and trying to get one estimate, but using this?
Yes, the point of combining the results. You know, the software doesn't know, you know, where in the model the plausible value was, the dependent variable and expansion variable. It's some equations for averaging some results in a special way. So yeah, we could, you could try. Even on this data, just make female a dependent variable and the plausible value one, the expansion variable, just flip it in the code. And well, yeah. No, I don't know, I think I wonder if you just average it, you just get an average, the point estimate. It feels more problematic to me just because the way measurement error works. I'll be interested to see what PISA recommended in that. Okay. No, it's good, really good question. I'll think about it. Okay, so that's what you should do. You see when it gets to the code, it's actually very easy to do, so we should do it. What are some of the other things that people do which are incorrect? You know, it's very tempting to go, I've got 10 math scores, I'll just average it and I'll analyze the average. Then I'm using all the data, right? Okay, so you can take the 10 math scores, add them up, divide by 10, you've got a new dependent variable. I've called it plausible value mean math. I'll just fit the model of interest. Okay. So here, that averaging process is averaging away the imputation uncertainty. You're destroying it, but it needs to be something to be respected, not something just to be kind of swept away. So again, the regression coefficients, and I should have the new slides, but you must tell me my errors. I should have plus beta 1 female in here. That's the model of interest. The regression coefficients will be unbiased, but the standard errors will be too small again. So again, you run the risk of false positives. Okay, that's not the case with female. It's always significant, but other variables, particularly school characteristics, they could tip it one way or the other. So here the standard error. So you can see the point estimate's minus 8.6. Okay, because we in model 3 where I've averaged the 10 plausible values to make my dependent variable. So I'm getting a point estimate which is very similar to what I got from Rubin's rules, which also used all the data. That's consistent. But my standard error is much less than for Rubin's rules, because I've averaged away the imputation uncertainty. And actually that 1.3 is actually, it's smaller than an analysis on any one plausible values, which were 1.5, 1.4. Okay, so this is also problematic. Well, that's another one not to do. And here the BPC has gone up. The act of averaging is kind of averaged away some of the measurement uncertainty. So this student variance has gone down, so that of what remains, it's more dominated by the school variation. So that idea is creeping in there as well. Yeah. So don't do that. And then the final model of this first session, just because we can, because this is an advanced multi-level course, we know about 3-level models, right? And when you think about it, each student's got 10 measurements. They've got a kind of collection of measurements, a cluster. The student's a cluster. So you need to reshape the data from wide form, where you have those 10 columns, to long form, where you've got 10 rows of data per student, like in panel data. And then the students within schools. So if you do that, I've used the subscript M. So M goes from 1 to 10, which are the 10 rows per student I, and the students within school J. I stacked my 10 plausible values in one column, which I called PV map. That's my dependent variable. Here's my regression model. The X variable is female. I've still got my school effect, my student effect, but now I've got a new lowest level in the analysis, which is going to be a residual, which is going to account for how the plausible values vary across the 10 observations per student. Okay, so it's the within student between plausible value variation. Okay, so that's the measurement error variance. Okay, when you look at the variance of these, that's the measurement error variance. Okay, so again, we're going to see kind of unbiased point estimates, but the standard errors will be wrong, too small. So this is model 4. So again, model 2 was Rubin's rules, correct analysis. Model 4, incorrect analysis. Again, we're getting out this kind of gender gap, which looks correct, minus 8.6, very similar to Rubin's rules. But again, we've got a standard error which is too small. And similar to the previous invalid approach where we just averaged imbalance as well. Now, ooh, big one, big boy. Gone, right, it's gone somewhere else. Here's the plausible value variance. Okay, so we've got 3 variance components now. But having adjusted for gender, this is the between school variance, the within school between student variance, the within student between plausible value variance. And you see this one here, and when in VPC terms, it's about 20% of the variation. Okay, which is again me saying that 20% is measurement error variance, which agrees, it all links together, right? You go back to the correlations of 0.8. That was also telling you that 20% is measurement error variance. So you're seeing it there. Okay. So that's also incorrect. It's fancy, nice 3-level model. Just that it's a more complex model doesn't mean it's better. It's not the right way of doing things. So yeah, the advice is apply Rubin's rules. Doesn't matter kind of what analysis you're doing. You just do the analysis 10 times. You get 10 sets of results, and you use multiple imputation, wrapper commands, and state or R to combine the results. And that is the summary, really. Don't do these other approaches, as tempting as they are. Don't only analyze one plausible value, apart from kind of model building and checking stuff out initially. Don't analyze the mean of the plausible values, and don't do this 3-level approach. Do that. Okay. Done the first topic of 4. Well done. Yeah. Right. So let's see where we are. So it is we now shift into state or R time. So I'll get you started, but I'll let you do a bit of that so you can have a break from me. It is 10:40, and we were meant to start the next lecture at 11:30. I think we'll start at 11:15 to give a bit more time for survey weights. Okay, but obviously, so in 35 minutes time, we'll start the next session. Within those 35 minutes time, you can do some state or R, and you can just leave the room, get a coffee, walk around, have a break. Okay, you use it how you see fit. I'll also come around individually once I've just shown you where the state and R materials are. Okay, does that sound okay? Okay, so let me stop the recording.